NASA's InSight lander just used Marsquakes to see inside the red planet, and what it found, buried at the core, completely rewrote what scientists thought they knew about how Mars formed. The interior of Mars is not what the models predicted, and the implications reach beyond Mars to how we understand the formation of every rocky planet in the solar system, including Earth. InSight, interior exploration using seismic investigations, geodesy, and heat transport, landed on Mars on November 26, 2018, in a flat plane called Elysium Planitia. It carried a seismometer called SEIS, the Seismic Experiment for Interior Structure, built by the French space agency SEIS. SEIS was the most sensitive seismometer ever deployed on another planet. InSight's mission was specifically to listen to Mars, to detect seismic waves, called Marsquakes, and use the way those waves travel through the planet's interior to map its internal structure, the same way seismologists use earthquakes to map Earth's interior. The instrument worked. Over its 4-year mission, SEIS detected over 1,300 seismic events before InSight's solar panels became too dust-covered to maintain power, ending the mission in December 2022. The first major finding concerned the crust. Seismic wave analysis revealed that the Martian crust in the InSight landing region is between 24 and 72 kilometers thick, with the best estimate around 39 kilometers. This is thicker than expected, and is divided into 2 or possibly 3 distinct layers. The thickness variation across the planet is significant. The southern highlands have substantially thicker crust than the northern lowlands, a hemispheric asymmetry that has been known from gravity measurements, but whose magnitude the seismic data helped refine. The mantle finding was the next revelation. Seismic waves traveling through the mantle provided information about its composition and temperature. The Martian mantle appears to be cooler and more rigid than models predicted, with a lithosphere, the rigid outer shell combining crust and upper mantle, that extends to a depth of approximately 500 kilometers. This is thicker than many pre-mission estimates suggested, which has implications for Mars's volcanic history and why Martian volcanoes grew so enormous. A thick, rigid lithosphere does not move, so a hot spot in the mantle keeps building one massive volcano in place rather than creating a chain of smaller volcanoes as the plate moves over it. Then came the core, and this is where the data genuinely surprised the scientific community. A 2023 paper in Nature, along with related studies published simultaneously, confirmed that Mars has a liquid iron core, but the core is larger than previously modeled and less dense than expected. The radius of the Martian core is approximately 1,830 kilometers, making it proportionally larger relative to the planet's size than some earlier models estimated, and the density is lower than a pure iron-nickel core would produce. The low density means the core contains a significant fraction of light elements mixed with the iron. The candidates include sulfur, oxygen, hydrogen, and carbon. The specific combination and proportion of these light elements affects the core's behavior, including how quickly it cooled, whether and when a magnetic dynamo could have operated, and how internal heat has been transported to the surface over billions of years. The absence of a current global magnetic field on Mars, confirmed by orbital measurements, is one of the defining differences from Earth. Earth's liquid iron outer core, convecting vigorously, generates a dynamo that maintains our magnetic field and shields the surface from cosmic radiation. Mars had a global magnetic field early in its history, evidenced by magnetized ancient crust in the southern highlands, but that dynamo shut down more than 3.5 billion years ago. The composition and size of the core revealed by InSight are helping scientists model why the dynamo failed, whether the core cooled too quickly, whether the light element concentration suppressed convection, or whether the heat flux from the mantle changed in a way that starved the dynamo of the energy it needed. The answers matter for understanding not just Mars but any rocky planet. The balance between core size, composition, light element content, and thermal evolution determines whether a planet maintains its magnetic field, and magnetic fields determine whether planetary atmospheres survive the solar wind. Mars lost its field, lost much of its atmosphere, and became the cold, dry world we see today. InSight decoded the interior of Mars one Marsquake at a time, and the planet's hidden structure is now the best measured of any solar system body other than Earth. Follow for more on what planetary interiors are telling us about the history of rocky worlds. And tell me, knowing that Mars's dynamo failed because of processes deep inside its core, does that change how you think about what makes Earth's magnetic field, and therefore life on its surface, possible?